Hello, I am Mallavan Ball, a fourth year PhD student at the Pennsylvania State University, and today I'm going to present my research on training energy efficient large language models leveraging equilibrium driven bio-plausible neural dynamics. Large language models are growing increasingly powerful, however, there is a substantial increase in their energy and power consumption. Our paper aims to address this issue, and we propose a novel bio-inspired spiking language model aimed at reducing the computational cost of conventional LLMs by mimicking synaptic information flow in the brain. Our framework leverages the average spiking rate of neurons at equilibrium to train a neuromorphic spiking LM leveraging implicit differentiation at equilibrium, thereby overcoming the non-differentiability problem that is inherent to training SNNs from scratch. We also develop a novel ANN to SNN knowledge distillation technique by which we use a pre-trained non-spiking language model to train our smaller student spiking language model. We evaluate our model on across various classification regression tasks of the glue benchmark. Unlike conventional neural architecture, in spiking architectures, the neurons communicate with each other using spikes instead of real values. Thus, the operations involved in a spiking model in general are floating point accumulative operations and not floating point multiplicative operations. This helps in creating simpler circuits and much more energy efficient design. This network is operated over a specific number of time steps as demonstrated here, and if we compute the average spiking rate, that is over a period of time we compute the number of spikes that is generated by a neurons and divide it by the number of time, we see that over a period of time it eventually reaches an equilibrium value. Now, the conventional method of training this SNN will be to use a technique such as backpropagation through time. However, this kind of a technique is much more computationally expensive because we need to store the entire computational graph. Leveraging this property of convergence of ASR, we can develop a novel training methodology by which we can use a technique called implicit differentiation at equilibrium, whereby we can only use the equilibrium value of the ASR to train our entire model. Thus, since we are using the average spiking rate and not spikes, we don't incur the problem of non-differentiability. Furthermore, there is also tremendous savings in overall training memory because we don't need to store all the intermediate steps. Our proposed model follows an encoder based BORD architecture. We support both integrate fire and leaky integrate fire spiking neurons. For the models whose results are shown here and is named as spiking bird 4, we use 4 spiking encoder layer, and each spiking encoder layer comprises of individual layer as represented here. The knowledge distillation framework uses a non-spiking teacher language model and the smaller student spiking language model. We allow the student model to converge to equilibrium as shown in this figure, and then we create an MSE loss with the intermediate layers of the student model and the corresponding layer of the teacher model. We also use two different variants of knowledge distillation, one for general knowledge distillation for pre-training the spiking language model, and also task specific knowledge distillation for fine tuning for specific tasks such as SST2 QQP of the glue benchmark. The results are shown here, and we have compared our model's result with other efficient implementations of language models. This is because our proposed work is the first spiking language model to be evaluated on the glue benchmark. The energy efficiency of the proposed spiking language model can be visualized through these graphs. Unlike conventional language model, spiking language model provides the opportunity to do a test time trade-off of accuracy and energy. Furthermore, we see that through the multiple control knobs, we can control the power consumption, which is directly correlated with the mean average spiking rate through modulating the tuning parameters such as threshold voltage, leaky factors, etc. We can see as the number of time steps reduces, there is an increase in the energy efficiency factor. However, the accuracy also drops by a bit. Thus, based on the current status of the HBS device or our requirement of accuracy on that specific task, we can choose to run our network for a specific number of time steps to get an optimal trade-off of accuracy and energy efficiency. In our future work, we aim to extend our framework to decoder-based GPT architectures. Thank you.